Friday is winter carnival, so there's no classes. So I want you to have at least one class to prepare for the first exam. So the exam will now be moved to Wednesday in class. The review class will be Monday, February 18th. It's optional, but if you have any questions, it's a good time to go. I will not be around later in the week. I had forgotten I had made travel because it was winter carnival. And so I will do the lunch review session today at Mission at noon, and the weekly dinner review session tonight around 5:30 in Mission. The exam will be on everything in your mathematical life up to and including Chapter 11, with, of course, an emphasis on Chapter 11, Calc 1 and Calc 2. I will not be putting on partial fractions and trig substitution, but integration by parts, bless you, stuff like that is fair game. Okay, I will send out a more detailed email about all of the stuff for the exams and everything. Because of the fire alarm last week, we actually, I know it didn't hit you, but it hit the other section, we didn't get to talk about some of the applications of what we're doing. And so at some point I'll try to show the Tron clip, but I wanted to talk a little bit about mathematics and art, in particular about lines. So we spent a lot of time talking about equations of lines, equations of planes. One of the great applications of this is for artwork. And so for the most part, I am a cultural Philistine. I was dragged to Mass MoCA on Saturday because there was a children's exhibit, and the day was saved for me by my 3-year-old daughter who looked at this from Sol LeWitt and said, "Daddy, Star Trek." And so I told her that is definitely worth an M&M. Now it's not quite right because it's not actually symmetrical in the Star Trek, but I now have a little bit more of an appreciation for modern art because of her. My favorite, though, piece is the following by Eakins. He was an American painter, 1800s, Philadelphia-based. And what I love about this is the story behind this painting. So again, I'm a Philistine. What I like about it is this math behind this. Eakins was using some revolutionary technology. He was using projection. And so one of the things when you're making a painting is you want to have people of the right perspective relative to the other stuff in the picture. And what was discovered is in someone's attic, they found a picture of these 4 people in the same pose wearing the same stuff on a road in New Jersey. And what they eventually realized is they looked at the painting and they noticed there were little dots in certain places around the people. What Eakins had done is he had taken the picture of these 4 people in a road in New Jersey and projected it onto the canvas and then put the dots so that he would automatically have the right perspective and sizes of the people without having to go through the trouble of calculating everything. And he didn't tell people that he was doing this because he knew how the art world would view it. And so, to me, this, I've posted a lot of this in the additional comments for Friday's class. There's a lot of wonderful things about this. How do you use technology? What is the definition of art? And what he was basically saying is, why should I spend all of my time doing these trivial calculations? Let me use modern technology to save some time. You can calculate all the equations of the lines and where things should be, or you can use projection to save some time. So at the end of the slides for today, I've listed what the homework problems are. Is there anybody who is not using the current version of the book? Is there anybody who has an older version? And if you all have the current version, then whenever I give page numbers and problem numbers, it should be correct. I will always try to include online the actual description of the problem. So if you don't have your math book with you, I can't imagine why you wouldn't want to lug this thing with you everywhere. You can at least start working on math at any moment in time. You can view it on your smartphone. It's wonderful. So the problems are described in detail here. They are also described at the end of the solution key. So always the solution keys will have what the problems are for the next day. Okay, so what I want to do today now is I want to talk about basically different coordinate systems and then start going into Chapter 12, which is the main idea of the semester. So how many of you have seen polar coordinates before? Okay, so the whole idea of these coordinate systems is different problems have different symmetries. And depending on what symmetry your problem has, you want to use a different coordinate system to make your life easy. So if you live on the surface of a sphere, and for practical purposes in this class, we will consider the Earth a perfect sphere, you really don't want to talk about things in terms of x, y, and z. Because if you're on the surface of a sphere, you're a fixed distance from the center. You want to basically say, hey, this is my latitude, this is my longitude. That's a much better coordinate system to use than to use x, y, and z. And there should be a way to pass from one to the other. This is what these different coordinates systems do. They allow you to exploit the symmetry of the problem. Okay, so the first one we do is polar coordinates. So polar coordinates. And so if I have something circular like this, I have the center, I have radius r, angle theta, here's my point xy. I can express xy in terms of my distance from the center and my angle measured coming up from the x-axis. And we get, by using trig, by using Pythagoras, we get x is r cosine theta, y is r sine theta. And this is just from, if I look at this triangle, this side here is just going to be r cosine theta, and then similarly, that side there will be r sine theta. So if you give me a r and a theta, I can give you an x and a y. Well, it makes sense that I should be able to convert backwards. If I give you an x and a y, I should be able to determine r and theta. Well, note that x squared plus y squared is r squared cosine squared theta plus r squared sine squared theta. Well, what's cosine squared plus sine squared? 1. So we just get x squared plus y squared is r squared. So we get r is the square root of x squared plus y squared. To get theta, if I take the ratio of these, notice the r cancels, and we get y over x is r sine theta over r cosine theta is tangent theta. Or theta is the arctangent of y over x. So while the arctangent may not be your favorite function in the world, you give me an x and a y, I can give you an r and a theta. So there's a nice transformation between the two spaces. I can write things in my x and y in my Cartesian coordinates. I can write things in terms of r and theta, my polar coordinates. There's one point where I have to be careful. There's one point where there are issues. What's that one point? So there's one point where there's a little bit of trouble. So we have a one-to-one map everywhere except one point. What point is troublesome? So if I take the center, what's the value of r at the center? 0. What's the value of theta? Any value of theta works. Right? If I want to get the point x equals 0, y equals 0, if r is 0, it doesn't matter what theta is. All the thetas will give you the point 0, 0. So except for the point 0, 0. So unfortunately, we have a little bit of an issue here. We're lucky that it doesn't really cause that much trouble, but it is something to be aware of. Every other point, it's unique. You give me an xy, there's a unique r theta. You give me an r theta, there's a unique xy. Okay, the next is cylindrical. So cylindrical coordinates is essentially taking polar coordinates and dropping them. Okay, so if you drop a circle, what shape will a circle sweep out if you drop it? A cylinder. And so we basically get x is r cosine theta, y is r sine theta, and then the very difficult z equals z. All right? And that basically just means, just allow the z coordinate to be anything. And if you look at what's going on, it's essentially what you would get as you sweep out a circle. Again, what's the only point that will be problematic? Where I'll have multiple points corresponding to the same point. 0, 0, 0, the origin. So again, origin is a problem. Well, we want to convert backwards. Well, converting from cylindrical coordinates is essentially the same as converting back from polar coordinates. We get r, bless you, is the square root of x squared plus y squared. We get theta is arctangent of y over x. And we get z equals z. So if I give you cylindrical coordinates, you can give me Cartesian coordinates and vice versa. So these are very useful for problems with cylindrical symmetry. The last one is spherical. Okay, and so you should imagine now that you live on the surface of a sphere. One of the annoying things is that often physicists and mathematicians, and sometimes even mathematicians have different notation for the same thing. And you have to be careful of which book you're looking at. So the mathematicians and the physicists often use different definitions for one of the angles. Sometimes what a mathematician calls phi, a physicist calls theta. So we need rho, theta, and phi. This is a distance, and these are angles. So you should think about it as you're on the surface of a ball. You have to tell me what the radius is. That's going to be rho. And you have to tell me the latitude, longitude. That's going to be related to theta and phi. Now, if you think about it, it might make sense. Well, why are we using rho? The Greek letter r. Why are we using that for the radius instead of r? The reason is we're going to do a trick and get spherical coordinates from polar coordinates. And so in polar coordinates, we use an r to represent the radius. So we're preserving the r to still be the radius for polar coordinates. Or at least this is why I believe they have done this. I would much rather use r for the radius and not rho. I have been outvoted by the ages. But I think it's because they want to keep the application of polar coordinates nice and simple. So we have to figure out how do we want to mark our angles. So imagine here's my x-axis, here's my z-axis, here's my y-axis coming into the plane. So again, up here is z, over here is x. I come down some angle phi from the z-axis. And now I'm at some height above the origin. And now what I can do is I can spin around in a circle, parallel to the xy plane, just a little bit higher. And as I spin this point around, it's going to trace out a circle. So I can get every point on the sphere by doing this. I choose some angle to come down, and then I spin around. So phi is going to mark how far I come down from the z-axis. So rho is the radius. Phi is how far down off of the z-axis. So I need to figure out what is my range of phi. What's the smallest distance I can move down from the z-axis? 0. What's the largest distance I can move down? This is tricky. So how far down can phi go? I'm sorry? Pi, excellent. Why not 2 pi? Why not all the way around?
It's just going to be the complementary angle.
Right, so if phi comes all the way down like this, and then I spin theta, I sweep out that circle again. And if phi only comes down here, and then I vary theta, I sweep out that circle. I want to make sure I cover each point once and only once. Well, I'm screwed at the origin. I can't do anything about the origin. But I can make sure that that's the only troublesome point. If I allowed phi to go past 180 degrees, past pi radians, I'd be sweeping out points multiple times. I'd sweep out everything twice. So we take phi from 0 to pi. We always mark things in radians. And then theta is going to be 0 to 2 pi. So unfortunately, phi and theta have slightly different domains. One is from 0 to pi, one is from 0 to 2 pi. Let's look at what's going on. Let's draw a good picture here. So I'm going to just redraw a little bit of my triangle. So if this is phi and this is rho, what's this length over here? So by trig, what would that vertical length be? So I've got a right triangle, so this is just rho cosine phi. And over here, this would be rho sine phi. And we call that r. So basically what's going on is I have polar coordinates. And now the radius is r, and now I just choose my angle. And the only difference now is instead of being in the xy plane, I'm now transported up. I'm transported up rho cosine phi. So we know, so it's now like polar coordinates with angle theta and radius r equals rho sine phi. So we know z is rho cosine phi. That's how high we are above the xy plane. And now we need to just figure out what x and y is. Well, we just use our polar coordinates. The only thing that changes now is the radius is now rho sine phi. So we get rho sine phi cosine theta, and then we get y is rho sine phi sine of theta. And so these are the spherical coordinates. You give me a rho theta phi, I give you an x, y, z. Well, whenever we calculate something, we should always check and see, is this reasonable? Can you think of any relation that x, y, and z must satisfy if it's on the surface of a sphere?
X squared plus y squared equals rho squared.
X squared plus y squared plus one more. Plus z squared, right? Because we're on a sphere. So check. Is x squared plus y squared plus z squared equal to rho squared? Well, x squared plus y squared plus z squared. All right. X squared is rho squared sine squared phi cosine squared theta. Wonderful. Y squared is rho squared sine squared phi sine squared theta. And then z squared is rho squared cosine squared phi. Right. Everything has a rho squared. That's good. We're trying to show that this sum is rho squared. Every term has a rho squared. Well, if we look at the first two terms, they both have a rho squared sine squared phi. Cosine squared theta plus sine squared theta is 1. So we get rho squared sine squared phi times 1 plus rho squared cosine squared phi. But sine squared plus cosine squared is still 1. And so this reduces to just rho squared. So it does check out. It does give us a point on the sphere. And so we can now write down the rest of the change of variables. If we want to go backwards, we get rho is the square root of x squared plus y squared plus z squared. We get, now if I want to figure out what phi is z over rho, and then I have to take the arc cosine of that, the cosine inverse. So it's arc cosine of z over the square root of x squared plus y squared plus z squared. And then last is theta, is if I take the ratio of these, the rho's cancel, the sines of phi cancel, and we get y over x is the tangent of theta, or just as before, theta is arc tangent of y over x. So you give me x, y, z, I can give you rho theta phi. You give me rho theta phi, I can give you x, y, z. I can go back and forth between the two. The only issue is at the origin. So the question is, why do we want to go through all this hassle of calculating things in different coordinate systems? Well, eventually you might look at differential equations. And you can write differential equations, how things change with time, using different coordinate systems. Or you might want to integrate. You might want to find what's the area of a ball, what's the area of a disk. And a lot of these integrations will be a lot nicer in different coordinate systems. So for example, how many of you know the area of a circle? This is the who's awake right now question, okay? So if you haven't been paying attention, this is a good time to raise your hand. Area of a circle is pi r squared. One of the things you need to know, okay? How do you prove it? Archimedes came very close to the method of calculus, very close to a good definition of limits by this method of exhaustion, by drawing polygons, regular polygons of more and more sides inside a circle and calculating the areas. And he did it inside and outside. He used a squeeze theorem to then get basically the area of a circle. If you want to calculate the area of a circle, here's one way to do it. Area of a circle. It's sufficient to just do the area of a quarter circle and multiply by 4. Well, if I give you a quarter circle, this is x squared plus y squared is 1, or y is the square root of 1 minus x squared. So you want to integrate from 0 to 1 of the square root of 1 minus x squared dx. To truly appreciate polar coordinates, do this integral. It's not fun. I urge you not to have fun. Play with it. Try to get this down. Okay? It can be done elementarily, but it's not easy. Polar coordinates makes this child's play. If you think about it, if you look at polar coordinates, if I want to have the filled-in circle, the radius goes from 0 to 1, theta goes from 0 to 2 pi. The filled-in circle in polar coordinates, and we'll talk more about this later in the semester, is actually just a filled-in rectangle. And if you let this be your r-axis and this be your theta axis, here's 0, 1, here's 0, 2 pi. A circle looks like a rectangle in polar coordinates. You can try to figure out what a cylinder and a sphere look like in cylindrical and spherical coordinates. If you want to integrate over nasty regions, be my guest, but I would prefer not to join you. I would much rather integrate over things like rectangles. And that's the power of polar coordinates, spherical coordinates, is they allow you to convert from these nasty integrals, with these horrible regions, to much nicer regions. Okay, so this finishes off chapter 11. Chapter 12, the first section is basically why do we care about differentiation? Why do we care about multivariable calculus? So we're going to be looking at functions of several variables. One of my favorites is from chemistry, the PV equals nRT. Pressure times volume is number of moles times the universal constant, R times the temperature. So if you know 3 of them, you know the 4th. Or you could hold 2 of them constant, vary the 3rd, and then the 4th is determined. And you get Boyle's law and Charles's law. I always forget which one is which. Okay, so you have all these different things you can do. You want to figure out how functions vary as you change the different values. So we're going to need a good way to graph functions. We're going to need a good way to talk about values of functions. One of the joys of calculus is to replace complicated functions with simpler functions. So this is section 12.1. Motivation. So if I give you some complicated function like this, what I can do using calculus is locally, I can replace my complicated function by a straight line. I understand straight lines very well. I can do a lot with a straight line. Complicated functions are beyond me. And so the whole point of differentiation is to take a very complicated function and replace it with a straight line and then somehow deduce things about the function from that straight line. So the standard example is you're in a car, you're driving, let's say, from Boston to Baltimore. And let's say I'm somewhere between New Haven and New York, say halfway in between. There's basically nothing. I am, of course, not speeding, so I'll be traveling at, say, 62 miles per hour. 1 second later, about how fast am I traveling? So I'm traveling 62 miles per hour. 1 second later, how fast am I traveling approximately? 62, Unless there's a truck that I just hit, I'm still going to be traveling at 62 miles per hour. Now I get into New York City. What's going to happen to my speed? Slow down. I'm going to have traffic and congestion. Locally, the tangent line does a great job. The question is, how far can you push this? And so you have a lot of estimates as to the approximation is this good over this region. That's one of the big things calculus tries to do. In several variables, what we want to do now is rather than approximating our function by a straight line, we're going to approximate it by a plane or a hyperplane. And this is why we spend so much time on vectors and planes. Because in several variables, you don't have a tangent line. If you have a function of 2 variables, you have a tangent plane. And you try to approximate this complicated function with a plane. All right, so this is the motivation for what we're going to be doing in chapter 12. All right, so 12.2 is definitions. So hopefully you've heard most of these terms before. There's a few different ways of defining some of the things, so I want to just be a little bit careful. So we're going to start off with the domain. So the domain of a function is all valid inputs. the range of a function is all possible outputs. And then the image of a function is the realized outputs. So for example, let's imagine I give you a function f from R to R. This means it takes an x in R as input and outputs f of x, which is some real number. So it takes a real number as input, outputs a real number as output. Let's say f of x is x squared. So what's the domain of this function? What are all possible values of x where this function makes sense? Yes? I'm sorry? All real numbers. So good. So its domain is all of R. What's its range? What are the possible outputs? So when you look at how it's defined, what are the possible outputs? No. That's the image. The image is 0, infinity. The set of all y such that 0 less than equal to y less than infinity. That's the image. That's the points that the function takes on. Looking at how it's defined, what are the potential outputs? It's more than just 0, infinity. The key word is potential. Any real number is a possible output. I say I have a function from R to R. All of R is possible. Which real numbers are actually outputs? That's the image. Okay? Typically, we're not going to really concentrate about range versus image. You should at least be aware of this. The difficulty is, until I actually calculate which values are obtained, it's going to be very hard for me to say what the actual image is. And so sometimes it's just more convenient to say, screw this, let's just, say, here is the potential range. And then maybe later we'll winnow it down a little bit. I could give you the function g from R to 0, infinity, defined by g of x is x squared. Is this function different than f? It has the same effect on inputs. The only difference is I say f goes from R to R, I say g goes from R to 0, infinity. So I've given them slightly different places as to where the output lives, but the effect is the same. So really these functions f and g are essentially the same. I'm not going to really belabor the issue here. I just want you to be aware of the notation so that if you're reading different books, you have a sense of what's going on. So now we need some examples of functions that are defined in different places. All right, so just so I use the same example as is in the notes, let's take 11x squared plus 2xy, bless you, minus 3 over x plus 4 over y squared. So the question is, what is the domain of this function? So I want to know what values of x and y do I have to stay away from? Yes?
You have to stay away from 0, but I think you can use any other number.
Good. So when you say stay away from 0, what do you mean?
Because you can't have 0 as a denominator.
Right. So which numbers do I have to stay away from? Just be explicit.
0.
But you have to tell me which pairs x and y do I have to stay away from. So a domain is all x and y in R2. So remember, R2 is just the pairs of real numbers, except those where, so when you say 0, where x equals 0, so is it and or? I think it's or y equals 0. If you say and, then x equals 0 and y equals 0 is just the origin. If either x is 0 or y is 0, then it's not defined. So it's an or, not an and. Okay? So as long as I stay away from 0 for the coordinate axes, this function is well defined. Here's a fun example. F of x is x squared minus 4 over x minus 2. So where's the potential trouble? So potential trouble at where? X equals 2. And so I'm being very careful. I'm using the word potential. Okay? Let's factor. If we factor, we get x minus 2, x plus 2 over x minus 2. Hopefully every fiber in your body is screaming at you to do something. What do you want to do other than run for the door and go skiing? Simplify. Cancel the x minus 2's. Right? If I do that, does this function make sense at 2? Yes, I'm going to use the word, it is definable at 2. So really, x equals 2 is not an issue here. Okay? And again, I'm being a little vague here. In a real analysis course, they'd be more specific. They would use phrases like removable singularity. Is this really the same function? Is this something like this f and g over here, where I have a slightly different function now, because the original thing maybe is not defined? Well, I have 0 over 0, but I have a very good 0 over 0. I can extract information from that. All right, let's say I give you the natural log of 2 minus x. What's the domain? Keep misspelling domain today. What would be the domain of the natural log of 2 minus x? X is less than 2. So we need 2 minus x to be greater than 0. So 2 is greater than x, or x is less than 2. I can't take the natural log of a negative number. Okay, let's do one last one. Example, this f of x is the square root of 4 minus 2x. So for the square root function, what do I need for the input? So if I have the square root of 4 minus 2x, what do I need for the input? I'm sorry? You can do a little bit more than positive. Positive or 0. So we need 4 minus 2x to be greater than or equal to 0, or 4 to be greater than or equal to 2x. So 2 is greater than or equal to x, or x is less than or equal to 2. So as long as x is less than or equal to 2, I'm going to take the square root of a non-negative number, and it will be well defined. So these are basically the key types of situations that you can run into when you're trying to figure out, is my function definable at a point? These are basically the types of issues that can arise. Okay. Any questions on definable functions? Okay, so what we're going to do now is we're going to move on to graphs and level sets. And so one of the important things to remember is there's lots of different ways of presenting information. At some point I want to try to have maybe a movie night and show you Flatland. I love the scene with the 4-dimensional cube being visualized in 3-dimensional space, projected onto a 2-dimensional screen. Eventually, you will come across this statement, there are lies, damn lies, and statistics. One of the few things I got out of all the English classes I took in my life is whenever you read a story, ask yourself, who is, I don't even know who versus whom, I didn't get much out. Who is telling the story? And why did the author choose to have this person be the narrator? Whenever someone presents you with information, they're trying to convince you. Look at which think tank is presenting the information. Who has commissioned the study? Different ways of presenting information will influence how you view the results. If there's time at the end of today, I will show you an easy way to manipulate you by presenting information. So I want to talk a little bit about graphs and level sets. So the graph of a function f from R2 to R is the following. It's the set of all pairs x, y, f of x, y. So it's all triples, f of x, y, with x, y, real numbers. So what I'm doing when I'm looking at the graph is I'm looking at, you give me a point, you give me an input, and I tell you how high up I go. How many of you ever had those old pop-up books when you were young? Where, you open it up, and then your picture comes off the page. Okay. If you actually still read a newspaper and you look at a weather map to see what the temperatures are, you're not going to get a pop-up newspaper where you open it up and you have a picture of the United States of America, roughly something like this. No, we have a lot of New Yorkers, in case we have anybody from Alaska or Hawaii. So the United States looks roughly like this. You're not going to have a pop-up map where above each point I'm going to go up to the temperature. How do newspapers show you temperature? Colors, right? Those of you who are freshmen may now be reconsidering choosing to do your studies in the Northeast. We're going to be the nice dark blue region, the cold region right now. We'll have sunny regions in other part of the country. Those will be the red regions. And so all the points that are the same color represent values of the function that are the same height. This gives you a way of presenting a three-dimensional graph in a two-dimensional space. Another way of sometimes doing this is with what's called level sets. So the level set of value c for a function f is all points in the domain that evaluate to c under f. So if you want, you can think of it as all places of the same temperature. Okay? And so, when you're looking at weather maps, there's lots of different things. You could look at the temperature, you could look at snowfall, which we'll be having for a lot of time. You could look at pressure. There's lots of different ways of looking at, values associated to longitude and latitude and assigning numbers. But we don't have a three-dimensional plot at our disposal. We can either do things like color, or we can do things like these level sets. So for example, imagine I give you, some part in the Williams area is going to look, one of the mountains is going to look something like this. And here's a way to roughly display this in a nice two-dimensional picture. Here's my first peak, maybe this is 100 feet, and here's my second peak, maybe this is 80 feet. And then maybe over here, this is the line of 90 feet. Over here, maybe this is the line of 80 feet. Maybe then here is the line of 70 feet. And then over here, maybe here's the 60 feet. And so if you look at something like this, you can get a really nice sense of what the function looks like in a two-dimensional map. You can see it's getting larger and larger and larger as I move up towards this point. You can see this point is not quite as high as this point. So this becomes a very convenient way of presenting information. And so I can give you different functions and ask you to compute the different level sets. So for example, let's say I give you the function f of xy is the square root of 1 minus x squared minus y squared, which I'll write as 1 minus x squared plus y squared. I think it's a little bit more illuminating if we write it like this. Okay? So the question is, what shape does this represent in space? Well, we often write, well, let's let z be f of xy. Square root of 1 minus x squared plus y squared. So as soon as you see something like this, you should have a certain urge. What do you want to do? So z is the square root. Okay, so to make it the difference of two squares, you're going to be squaring things. So you want to get rid of the square root, exactly. So we have z squared is 1 minus x squared plus y squared, or x squared plus y squared plus z squared equals 1. But remember, z has to be greater than or equal to 0. All right, x squared plus y squared plus z squared equals 1, z greater than or equal to 0. What region is this? It's a sphere. Okay, is it the entire sphere? Do we have the whole sphere? We have the upper half. If we had the whole sphere, I wouldn't have this restriction, z is greater than or equal to 0. So I have the upper half sphere. the northern hemisphere. And so if I want to try to plot it, it's going to look something like this. Okay? Let's try to plot this using level sets and see how the level sets can allow us to get a really good picture. So, plotting by level sets. Okay, so we want to look at f of xy equals, the square root of 1 minus x squared plus y squared equals c. So the question is, what possible values of c can we take? Could someone give me a possible value of c that cannot happen? That there will be no x and y that will correspond to that value of c? Yes? Negative 1, right? The square root can only be non-negative. So we can't have c equals negative 1. So more generally, we can't have what? Negative numbers. So level set is empty if c is less than 0. Great. We've now handled half of all the values of c. All right? There's another large class of c that we can immediately kill and say they lead to something that cannot happen. So we couldn't have c less than 0. I claim there's an, yes?
It can't be greater than 1.
Good, c can't be greater than 1. The largest this can be is when x squared plus y squared is 0. So the square root can't be more than 1. So if I give you a value of c greater than 1, if I give you c equals 2, there's no value that would work. If I want c to be 2, I need to have the square root of 4, so I need x squared plus y squared to be negative 3. Right? You give me any longitude and latitude, it's not going to square to negative 3. So level set is empty if c is greater than 1. So now we just have to study what goes on when c is between 0 and 1. Okay? So now, let's assume c is between 0 and 1. So we'll come back over here. We'll keep the definition of level set up. So assume 0 less than equal to c less than equal to 1. And I want to find what values of x and y correspond to this. So I want f of xy square root of 1 minus x squared plus y squared. This is supposed to equal c. All right, so if I square, in the interest of full disclosure, I did not square this correctly at 10 o'clock, it would be c squared. So if I just rearrange the algebra, I get x squared plus y squared equals 1 minus c squared. What does this look like? X squared plus y squared is some constant. What geometric shape is this? Circle. So I'm going to write this as x squared plus y squared is the square root of 1 minus c squared squared. So it's a circle of radius square root of 1 minus c squared. And notice that this radius makes sense. C is between 0 and 1, as 0 less than equal to c less than equal to 1, radius is between 0 and 1. And in fact, now you can see why we couldn't have c less than 0 or c greater than 1. Okay. So now, what does this mean? So you give me a value of c, the level set is going to be all points x and y, such that x and y are on a circle of radius 1 minus c squared. So, again, this is the graph. And now, let's try to draw the level sets. What's the easiest value of c to take?
0.
I would disagree. I'd say that's the second easiest. I'd say c equals 1 is the easiest. That gives me x squared plus y squared is 0. All right, x squared plus y squared equals 0. That's just the origin. So c equals 1 corresponds to the origin. If I take c equals 0, I get x squared plus y squared equals 1. That's a circle of radius 1. So here is c equals 1. If I take c equals 1/2, I get x squared plus y squared is the square of the square root of 1 minus 1/2 squared. Okay, 1 minus 1/2 squared is 3/4. So it's a circle of radius square root of 3/4. So here would be c equals 1/2, and the radius would be square root of 3/4. Question?
Is the outer circle where c equals 0?
Oh, yes, thank you. Yes, c equals 0, thank you. So what you can do is you can get a really good sense of the region by looking at this plot. Here's the highest point. It's symmetric, and I'm getting just these different circles. Now, to see that this is actually a hemisphere is a little bit harder. You'd have to have some idea of how the spacings are going. But you can get a sense of, the degree of symmetry of the region. The highest is at the center. It's falling down symmetrically. Once you get to a circle of radius 1, you no longer have anything beyond that. All right. So I want to just do one last comment about level sets and then give you an example of how to be misled. Another way to view the idea of a level set is to imagine you have a piece of paper parallel to the xy axis. And what you're doing is you're basically sending that piece of paper through your graph. And you're looking at all the points that it hits. And all the points that it hits, you then look down, you project down into the xy plane, and you see, what are my inputs that went up to this level? So if the level is 0, you get the outer disk, and as it moves up, you get a smaller and smaller circle, until when you get here, you get a point, and when you go higher, you have nothing. If you go below the xy plane, if you take c equals -1, -2, -3, you see there's no points that work. Okay, any questions on level sets? So again, it's a good way to visually present information. There's lots of different ways to present information, and I want you to be aware of the differences. So, fun fact, a team has won 3 of their last 4 games. Is the team playing well? Now, this is Williams. I know a lot of you are on sports teams. You've won 3 out of your last 4 games. Are you playing well? Yeah. What's your winning percentage? 75%. Seems pretty good, right? Winning percentage of 75%. That sounds good, right? I'm going to show you that you're actually not nearly as good as you think. All right? And I'm going to do this without even knowing what sport it is, what team it is. 1, 2, 3, 4. Here's the last game. Last game -1, last -2, last -3. I've told you you've won 3 out of 4 games. What happened 4 games ago? Only 2 possibilities, right? You lost. Really? If you lost 4 games ago, then you would have won your last 3 games. What would I have said in this case? Would I have said you've won 3 of your last 4? No, what would I say? You've won your last 3. So because I say you've won 3 of your last 4, we know the last game is not a loss. What's the last game? Has to be a win. So somewhere in these games I have 1 loss and 2 wins. Let's go backwards. What must have happened over here? Loss. Why? I would have then said you've won 4 out of 5 games. So because I said you've won 3 out of 4, I know this has to be a loss. All of a sudden, we have 2 losses, 3 wins, 60%. you expect an average team to be 2.5 or 50%. You're essentially average. Okay? But by saying you've won 3 out of 4, I'm trying to frame the conversation. I'm trying to get you to look at something important. Sadly, this is more useful than most of what I'm going to teach you for the. Oh, please turn off the camera. This is more useful than. This is more useful than most of the multivariable calculus I'm going to teach you. It's very easy for you to be misled by statistics. Politicians will do this all the time. Companies will do it all the time. Look at the information being presented. Remember, ask yourself, who is giving you this information? Why have they chosen to present this information to you and not something else? All right, so there will be reviews today at Mission at noon right now, as well as Mission at 5:30. I will be